Hello, in this video we are going to talk about Newton's second law for rotating system. In the translational form, which we did in Unit 2, we had F net was equal to mass times acceleration. That's for translation. Now for rotational, the net torque is equals to I of the system multiplied by alpha, which is the angular acceleration. So that's for rotational. So in that case, you can see that the net torque is not equal to 0, alpha is not 0, and I, as we know, if it's rotating, definitely is not going to be 0, and V or omega is not constant. Now we can solve, going to do two examples with what we call them the Atwood machine. The first one, if I have a flat surface, I have object 1, M1, is connected by a rope through a pulley or Atwood machine to M2. And this is M1. Let's say here I have a force of friction. Here we have T1. Here we have T2. And we have FG2. And before in Unit 2, we considered the pulley to be, or the Atwood machine to be of negligible mass, so we couldn't take it into consideration. Now this pulley, for the pulley or the Atwood machine, I is going to be half m r squared, since it has a radius and a mass, and that's what we derived in the previous one in 5.4, the moment of inertia for a pulley. And it's going to have an acceleration alpha. We want to find what is A, an equation for acceleration. We are going to start for first m1. F net is equal to m1 or F net 1 m1 times A, and the forces here, they will be T1 minus the force of friction is equal to m1 times A. And we know that the force of friction is going to be mu times m1 times g. We can replace it, so it will be T1 minus mu m1 g is equal to m1a. So that's going to be our first equation. Then we are going to do it for m for m2. Again, F net 2 is going to be equals to m2 times A. So we have Fg2 minus T2 equals to M2A. That's what we have done in unit 2. But in unit 2, since the pulley was massless, T1 was equal to T2, but here that since we have the pulley, it's not going to be the same. So right now that's the second equation. Now for the pulley. Now we can try to draw it. I have T2 is going to rotate it in this way, and that's going to be T1, and I have a radius R. So we see that T2 and T1, they are going to rotate it in opposite ways, but since it's going to go rotate that way, so it will be T2 minus T1. So for the pulley, it will be net torque equals to I times alpha. What are the torques? It's going to be R times T2 minus R times T1 equal to 1 over 2 m mass of the pulley times R squared times alpha. Now we know that alpha is A over R. So from before, alpha is equal to A over R. Why I need this? In order to make sure that I have also A's as we've had here. So that would become R T2 minus R T1 equals to half M R squared A over R. On the left side, we can take R as a common factor. R into T2 minus T1 equals R squared, and R I'll remain with 1R, so half M R times A. Now again, R and R, they will cancel, so we remain with T2 minus T1 is equal to half M A. That's going to be our third equation. So our three equations are, for now, T1 T1 minus mu M1 G is equal to M1 times A. The second equation is FG2 or M2 G minus T2 is equal to M2 times A. And the third equation is T2 minus T1 is equal to half MA. So those are equations 1, 2, and 3. If you remember in unit 2, we said we are going to add the equations. It will make it simpler. That's the reason why it will make it simpler here. So if I add all three equations, if you notice, T1 and minus T1, they cancel. So 1 plus 2 plus 3. T1 and minus T1, they cancel. T2 and minus T2, also they cancel. So I remain with M2G minus mu M1G equals to A, can take here A as a common factor, into M1 plus M2 plus half M. From this, we can find what is mu if you want. If there's no mu, no friction, this one will be cancelled. The second term will be cancelled, and we can find whichever we want. So for acceleration will be equal to M2 minus mu M1 into G as a common factor over M1 plus M2 plus half M. Notice that if I exclude the mass of the pulley, I get to what we got in unit 2 for the acceleration terms. I can, sometimes they may tell you there's no friction, we cancel the mu m1. If the pulley is massless, we can cancel half m. So that's going to be our general equation. Now we can go over another case. If I have a pulley and we have here, let's say M1, here M2, and the pulley has a mass M and radius R. Again, we can do the same thing here for 1, 2, and 3. Let's say it's going to rotate that way. So M2 is heavier, M2 is greater than M1. Again, we are going to start with Newton's laws. Here I have T1, we have FG1, we have T2, and we have FG2. So what do we have? Again, T1 minus FG1 equals to M1 times A. That's the first equation. FG2 minus T2, since it's going downward, is equal to M2 times A. That's 2. Now the pulley equation is going to be the same as what we have done before. So it's going to be T2, just the same as what we got this one. It's the same derivation. So we end up with T2 minus T1 is equal to half M times A. That would be our third equation. Again, the third equation 3, it's the same derivation as what we have done here for the pulley. Or you may hear it as Atwood machine. Now again, same thing. 1 plus 2 plus 3. T1 and minus T1 they cancel. T2 and minus T2 they cancel. So what we remain with? Fg2 minus Fg1 is equal to A into M1 plus M2 plus half M. So A equals Fg, we can replace it by Mg, up to you, either or. So if you want M2 minus M1 into G, that's if I put Mg and Mg and take G as a common factor, equals A into M1 plus M2 plus half. So A will be equal to M2 minus M1 G over M1 plus M2 plus half M. Those are the two general equations or general examples of Newton's second law, and you see they can be very similar, but here we have the coefficient of friction. That's it for 5.6.